Again, test is on block day. Worksheets 1 through 3 are due on block day. Graphing 4 to the x. Now, picking the x values is important here because if you pick some crazy stuff, you end up with, 4 to the 4th, and I don't even know what that is. Even 4 cubed is 64, and that's way off the graph. So let's pick some smaller values. Let's go -1, 0, and 1. For the -1. What's 4 to the -1? 1 over 4. What's 4 to the 0? 1. And 4 to the first is 4. Well, that was pretty easy. Let's plot those points. So -1, 1/4. 0, 1. And 1, 4. I don't know if that's enough for you to know what the picture looks like.
It's one of those that do like that.
Yes, it's one of those things that goes like that. Those are the only 3 points I need to see. Since it's the first one, let's go ahead and plug in 2 and see what happens, just so we get a better feel for this graph. So what's 4 squared? 16. And so that's, way up off the page here. So this thing, when it turns sharp and quick. What about -2? 16 in the bottom, so 1/16, which is really, really hard to show the difference between 1/4 and 1/16 on graph paper this small. But you get the idea. And then 4 cubed would be 64. That's way off the paper even. And then 1/64th, you basically putting the dot on the x-axis there. So when you graph them, I'll be looking for 3 key points. If you want to do more, you can, but usually you really can't because they end up off the page or so small you can't do anything with. So there's our graph of 4 to the x. Now for number 2, let's use our parent function knowledge. And so even though we haven't done one of these before, tie it to something we do know. When you see x minus 2, what does that usually do to the graph? Move it 2, which way? To the right. So we'll move it right to from 4 to the x. So we look back at our 4 to the x graph or table. And some people will redo the table, other people will just sort of in their head shift the graph to, and that's fine as well. So right 2 means -1 goes to +1, 0 goes to 2, 1 goes to 3. And then I'm not changing my y's because I did not move it up or down. So there's my new table of values. So I didn't, if you just walked up and looked, you wouldn't know where that came from. I didn't so much build it from this function. I took this original function and I went right to. So it's easier to do it this way because that way, once you come up with one graph, then you can apply the stuff you already know, the parent function transformations. So 1, 1/4, 2, 1, 3, 4. And so just like the parent functions, it looks the same, it's just been shifted to the right too. Thank you. So, in my mind, these aren't too bad because we will always ask you the parent function first. And so you take that one nice and slow, plug in points, get a nice graph, and after that, you can use your parent function rules. Speaking of parent function rules, -5 at the end, what's that going to do to the graph? Down 5. So in terms of our table, which variable should we alter and how so to move it down 5?
-5 on y values.
Yeah, so we'll take the y values and move them down. So the x values are the same. 1/4 minus 5. Come back to that in a minute. 1 minus 5 is -4. 4 minus 5 is not -5, is -1. Okay, 1/4 minus 5. You can do the common denominator thing, and that's fine. You could just know that 5 minus 1/4 would be 4 4/5, but negative. But you can also sort of use the down 5 thing on the graph. So normally we're at -1, 1/4. Zoom way in here. So one way to accomplish this down 5 is to sort of not worry about the table and just from the graph go down 5 from each point. So start there, down 1, 2, 3, 4, 5. And so if adding or subtracting fractions messes with you, you can kind of avoid it. Just move 5 spots down on the graph. Now, hopefully 1/4 minus 5 is not that big a deal. It's -4 4/5. But again, you can do it graphically if you'd rather. 0, -4, 1, -1. And there's our graph. Questions on that one? If you are the graphical type person and you want to just look at the two graphs and rather than make the table, just take each of those points and sort of visually count down 5 spots from each one, that's okay. But at least showing your work then would be telling me that you're moving them down 5. So I don't need to see the table if you're comfortable without it, but I need to you need to tell me what you're doing. That's down 5 and then do the down 5. Number 4's got a negative in there. That flips it, but which way is it flipping? Is it a left-right flip or an up-down flip? Why do you say left-right? Because it's on the x, so that's going to be a left-right flip. And same thing. I'm going to adjust the table. Some of you will just visually look at the graph and switch it left and right, and that's okay as long as you can do that correctly. So I'm going to change the signs of my x values. So I change my x value signs. And graph those points. So I like to do the table and then use the graph to sort of confirm what I already said was going to happen. That's a left-right flip. Now, what we didn't ask on all of these, what we might want to think about. So let's back up to the first one. There's an asymptote. On that first one, can you tell where the asymptote is? especially if you think about -2 1/16. What are we getting closer to? Okay, you answered my question. We're getting closer to 0. What's the asymptote?
Y.
Yeah, y equals 0. You don't have to graph it. Sometimes we'll ask for it, sometimes not. How about on number 2? What's our asymptote on number 2? Y equals 0. Because if we start with y equals 0 and we move it right 2, it didn't really change. It did not change our asymptote. So the parent function thing affects the asymptote, or it doesn't affect the asymptote. So like number 3, if we go down 5, what's our new asymptote? Y equals -5. And then on number 4, if we flip it left and right, our asymptote is still y equals 0. Number 5. So it's kind of a big break between 1 through 4 and 5 through 8, because our base is not 4 anymore, it's e to the x. Let's start the same way. X, y, -1, 0, 1. Do you remember what e is equal to? Like what number e is?
Isn't it if you do it the second time, some big number?
2.6 is close. It's 2.7. Now, for purposes of graphing, 2.6 would have been plenty close enough.
When do you use what? When do we learn that?
We learn it with when you did.
If we did that this year?
I don't know that we've done e this year. Use it in that interest formula. Yeah, usually a equals pert. That's right. So you've seen it before. Basically, for our purposes right now anyway, you just need to know that it's about 2.7. Sort of like pi is 3.14, even if you don't know what it's used for, although you probably have a better understanding of pi when you do e. So 2.7 is good enough. So e to the -1 is 1 over 2.7, which I don't know what that is, but I can still graph that because while we're estimating things, that's pretty close to 1 over 3. Certainly close enough when our graph is this small. What's e to the 0? 1. That one we can get for sure right. And then e to the first is 2.7. So it's kind of the same graph as above. It's just not, the turn isn't as sharp because the base isn't as much. All right, number 6, think parent functions. E to the -x. What does that do to the graph? Reflects. More detail. Careful, don't say over x, because that would mean an up and down. You reflect the x coordinate, so it's a left and right So be careful about reflects over X. It actually reflects over Y, but I don't like that terminology because that seems confusing. I would just like to say it reflects left and right because the X variable is negative.
Do we need to write that down?
I would write that down. That way, especially if you're not going to write the table down. Again, some of you are going to just look at the first graph there and just sort of visually reflect it. And if you can pull that off, that's fine. Some of us need to write the table out again. So I like to write the table out, graph it off the table, and then use that reflects left and right as kind of a check. So write the table, draw the graph, and then check that, yes, that's a left-right reflection from what we started with in number 5. Uh-oh. Why uh-oh on number 7? Yeah, 2 things going on. So what's the plus 5 do? Left 5, and what's the minus 7 do? Down 7. So left 5, negative 6, negative 5, negative 4. So left 5. Down 7 means I'll subtract 7 from all my y coordinates. Again, 1/3 minus 7. You can either start at 1/3 and count down 7, or you can do the fraction work there. 1 minus 7 is negative 6. 2.7 minus 7 is negative 4.3. Or you could do the same thing. You could just start at 2.7 and count down 7 spots. But with 2 transformations on there, that's kind of tricky. So negative 6, 1, 2, 3, 4, 5, 6. Negative 6 and 2/3, 1, 2, 3, 4, 5, 6 and 2/3. Negative 5, negative 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Negative 4. Negative 1, 2, 3, 4 1/3. Okay, only 3 points. They're kind of close together, but we know what the original shape looks like, so I can still sketch in what e to the x looks like. Right, number 8. What's that negative do? Yeah, it reflects in the y direction, so it reflects up and down. Technically that means it reflects over the x-axis. I think it's confusing to phrase it that way. I'll just say it reflects up and down. It changes the y coordinate. So all my y values are negative now. Just copy them down from the original table. Nothing changed with the x values. Negative 1, 0, 1. So I'm going to graph it off the table and then see if my graph is indeed a upside down flip from where we started. Yep, that flipped upside down. again, and if you look in your, we're not quite done yet, but if you look at the worksheet, we give you the parent function to graph first, and then we ask you to make changes off of that. So make sure you get that parent function down correct. Plot points, go slow, be careful, and then use your parent function rules to slide it around or flip it or whatever you need to do for it. Consider f of x equals e to the x. So, domain and range, it's nice to see a graph to think about that. What's the domain of f? What x values does that graph cover? Yep, all of them. Another way to say that is you can plug in whatever you like for x and you'll get an answer that works. How about the range? What y values does it cover? It goes to infinity. Good, 0 with the parentheses. Why the parentheses? Because it doesn't equal 0, right? That's the asymptote. It gets closer and closer. So it didn't really ask about the asymptote, but that's a kind of a parallel question there. Those go together. Name 3 points. Well, that's the table of values we started with. -1, comma, 1 over e, 0, 1, and 1e. If you put 1 over 2.7, that's fine, and then 2.7 for e, that's okay. Let's see, x-intercepts, that would be where y equals 0. Or where it just, we got a picture. Where does it cross the x-axis? Nowhere, none. How about the y-intercepts? Where does x equal 0? 0, 1. We've already listed that point. We've graphed that point. So those last questions are more about reminding you of some vocabulary things. Domain, range, x-intercepts, y-intercepts. All right, today's assignment is worksheet 2. Again, don't get behind because these are first 3 are going to be due on Wednesday. And so this is not one of those times where you have 3 bonus days thrown in to just put it all off to the end and do it the night before. I mean, I guess you could still do that, but the night before is going to be Tuesday night, if you phrase it that way. Put it in your language there. So keep up with them. Please try some of these because tomorrow we're going to graph logs, and that's a little trickier. But it's based on graphing exponents. So if you can graph exponents, you can graph a log.